Okay. Okay, guys. Let's get started. First, welcome everybody to here. It's nice to see people gathering together in summer like this. Today we are happy to have Professor Sota Yoshida from Japan to give a nuclear theory seminar here. And just a bit information about him. So he had his PhD degree at 2020 from University of Tokyo, and actually before that, like between 2019 and 2022, he worked as a research associate at this university called Utsunomiya University. Is that right? Yes. And then between 2022 and this year, he was assistant professor, and now he's an associate professor at the same place. And he has a lot of interests covering nuclear structure, shell model, ab initio, first principle calculations, and also quantum computations, and statistics, and all kinds of things. And now I'm going to let you take away.
Okay. Thank you for kind introduction to me, and I would like to thank Heiko inviting me to here. So this is much pressure to be here. I mean, so my dream come true. To be honest, I'm a big fan of your YouTube channel. I have been watching on your talks and learn many things from it. And please click good button if you like it, or even if you don't like it. Okay, so I'll be talking about this, and before going into the main topic of this seminar, let me kind of do introduction about more about my city. So, how many people in this room have ever heard the name of city Utsunomiya, other than my institute? None of you? Heiko?
Well, yeah, because.
Okay, so none of you, right? So I will be rewarded by my city for this advertisement. So Utsunomiya is located around here in the Tochi prefecture, north to Tokyo, and it is the location is kind of 100 kilometers away from Tokyo. And if you take a super express train, you can reach Utsunomiya from Tokyo less than 1 hour. So and the population is not so big, but the kind of 34th of the Japanese city. So and we have more than 500,000 people, and we are surrounded by very nice nature. I mean, mountains and lakes, and no sea, but you can find very nice temples and shrines. So it's very nice place to visit. So if you have some chance to visit Utsunomiya, so please call me. Okay, so on the Chirin introduced me. I mean, I started to work at Utsunomiya University from 2019 before getting PhD, and it's a kind of tricky in Japan, but I did. And I was promoted in this April because we have launched a new faculty. I was kind of lucky, so please for my job, accidental associate for this. Okay, so here's our outline of today's talk. I'll be talking about mainly two things. The one is about the Julia package for nuclear structure calculations, which I made, and I have been working on this couple of years. And the second one topic will be the surrogate models for IM-SRG from two perspectives. One is from machine learning technique, the other one is dynamic mode decomposition, and then some reports. So let me begin with this first one. So NuclearToolkit.jl is a Julia package I made, and this consists of mainly the four building blocks, and the color EFT part, help you to make some the kind of potentials, mainly NN potentials, and the Hartree-Fock part covers the kind of the interface for many-word calculation, like Hartree-Fock MBPT or novel ordering stuffs, and the IM-SRG part supports, of course, IM-SRG part and the Barron space counterpart, and I should mention that the functions are only prepared for the scalar operators for now, but it's provide the kind of interface to try IM-SRG in the easy way, and this has some functions for emulating IM-SRG, and I will talk about it later. And the shell model part is actually the first package I made in junior language, and so it's not much like a Julian way. I mean, this is kind of lengthy, but it provides us kind of a unique interface for test eigenvector continuation within the context of Barron-Sierra calculation. And in total, the total number of lines of this package is around 20,000 lines, including the doc strings to make documents. So what do you think about this number compared to your own made code? So there are several motivations for me to develop this dual package. So our single method or code, numerical code, can be very lengthy in many cases. Or I don't know what is a typical number, but this could be kind of the typical number for that. And it is very hard, at least to me or a younger student, to understand them or learn them properly. So, so people in conferences may sometimes say, "Oh, what you have to do is just solving this program with our method or something like this." And I was like, "How can I do that?" I don't understand the complete procedure for it or how to prepare the metrics to be diagonalized. So I was like kind of depressed in the conferences. So yeah, that's the motivation for me to develop this code and share this code in public. And the research, I think the second part is my opinion. I mean, research methods are sometimes kind of clusterized or localized to specific groups. So if you want to use that method, you should be you should belong to them, or you should. This can happen. I mean, this is a cartoon showing the favorite my joke. So in Japan, we have a kind of culture of secret sauce or secret soup in the Japanese restaurants for example, eel or pork cutlet or ramen, whatever. And the same thing can be happened in the research community. I think the secret sauce code can be seen in some group. Of course, I'm not saying that is bad. I'm not saying that. I do understand the situation. I do understand the reason, but I just naively thought there would be kind of benefits to open my code to the community to help someone like or me struggling with the nuclear manifold complicated nuclear manifold methods. So, and we may have some lessons from the other communities, like machine learning community. I mean, nowadays people are using the machine learning in many fields, other than nuclear physics. Or the reason, the part of the reason is, I think, the machine learning techniques are developing very fast. This is partly because the many people are using those. So we may have some lessons from that. So and of course, the education is very important factor to develop code. I mean, there to share some ideas with younger people. So that's why I started to make this package and opened it. I would say, so here I listed some of the code shared in our community. I cannot list them all, so this is just a part of it. But the numerical code listed here have inspired me a lot to develop my package. So I really appreciate the author's open-mindedness to share their code with us, and you and your code have brought me here today. Okay, so you may think why I chose a Julia language for this project or this package. So these are mostly from the official website of the Julia language. So these are the advertisement, kind of. So don't take it seriously. So the important feature to me is Julia has own package manager, and we sometimes, how to say, suffer from the resolving the dependencies. So code A can be run in my laptop, but the code cannot be run in your system or your cluster machine, so that happens. So, but I would say dependencies of the packages in Julia are under control. I mean, the dependencies are resolved in a clever way. So I'm not saying that Julia is our best language for the nuclear physics code. I mean, I just mean to say the Julia is nice for me, and would be nice for the younger student to learn or to implement something new by yourself. So here, this schematic shows their code development workflow with GitHub Actions. So if you make some changes to the code or document, the changes will be pushed to the GitHub repository via pull request, and GitHub Actions will execute test code with specified OS or specified version of Julia, and the generation and deployment of the document are automatically done. And this may mitigate the risk of kind of disruptive changes or releases. And then you will get the terrible update code and the document, and you can play with that. So this cycle may be good for, to avoid the disruptive changes during the code progression. And I have to say the documents are available through the repository. If you click this part, you can get this kind of documentation. And these are actually generated by their Julia package. I mean, Julia has their document.jl for generating and deploying the document for you. And just what you have to do is to prepare some doc strings in the markdown format to explain your code, and then the package will assist you to deploy this kind of documentation. And you may think that writing document codes or test codes are not your job, but I would say it's not costly to do that nowadays. I mean, for example, you can use the GitHub Acquire or some other similar extensions like this based on the large language model. So they will assist me to make to construct the document or test code. And this is a funny example for the Python case. If you write the code does nothing, and they type in the quotation and the function and the GitHub requirement will propose you the explanation about the code, and you will get something like this function that's now. And this example is actually generated by the GitHub Copilot. I mean, these are generated by reading this or the content. I mean, in the GitHub Copilot, it reads all the codes in the same workspace or in the same directory. So, which gives them the context. So they will, how to say, they propose a nice document or nice test code for you. So it'll be very helpful, at least to me. Okay, so this is kind of the manual page for my package. So let me go through it very quickly. The point is the installation of Julia language and the installation of packages are very easy. For example, if you want to try my package, all you have to do is in Julia level. I mean, so you just do that, typing the parentheses and the add package name. That's it. So you will prepare this with the packages. And the package must have this kind of the dependency files to resolve dependencies. So it helps you resolve dependencies. And you can create your own Julia environments or your Julia project anywhere. And for more details, please see the Julia document. And if you want to try some packages in Julia, the test code will help you to understand how to run the codes. I mean, if you just type the test package name in the package mode of Julia, you can test you can run the test code preparing the package. In this case, I show the test result of my package. So if you just type this, you will learn these codes. I mean, generating current potentials or using them. MP calculation can be done, or IM-SRG or VS IM-SRG calculation are done. Or after that, you can obtain the kind of effective interaction for the shell model input, and you can try the shell model functions and also eigenvector continuation stuffs. And also you can try the more, how to say, the fancier things for generating input for the quantum computation, for example. And okay, so if you're interested in the package, please tell me. I mean, so all you have to do is to just write using NuclearToolkit and prepare your code in your nice code for your project. So I'm staying here until Wednesday, so please contact me if you want to know more about this package or Julia. Okay, so for this is the first one. So questions, or will we? Do you have any questions?
So you make you rewrite all the code with the Julia, or you can you make some library for example, the IM-SRG or the Carol potential stuff. You can make it to library, and you can make the interface with the Julia. Actually, you can call the library of that one. So which will be.
Could you say?
I mean, you can do both, right? You can rewrite all the code by yourself with the Julia,
Yes.
or you can also make the interface to all of these codes. So,
Yes.
Which one?
I did. What I did here is just sort of actually not rewriting the existing code, but this is not the kind of wrapper of the existing code by others. I mean, the all things is written in Julia way, I think. Does it make sense?
So I didn't. So you just saying that you just make a wrapper or something?
No. I implement these by myself
Okay.
with this small number of runs.
Nice.
Is there? Okay, so let me move to the second part. Okay, so next topic will be our emulating IM-SRG, immediate similarity renormalization group method. So let me, so it is kind of pressure to introduce IM-SRG here in front of you, but I will try it. So IM-SRG is an operational method, and you can, so the basic idea is the transformation of your Hamiltonian as a function of 4-parameter S to decouple or to transform the Hamiltonian to be the one can be handled more, how to say. So the basic idea is to decouple of the P space and Q space. This can be, for example, core space or on particle space. And of course, this partition is not limited to particle and cores. You can apply this to the partition between Barnett space and the others. And then they usually keeping up to the normal order tubular part leads to the terminology IM-SRG2 approximation, and like this, and so decoupling between so you can, for example, obtain the expectation value of the Hamiltonian, the energy in more, how to say, the compact form by this IM-SRG transformation. So this schematic picture is from the review of the latter paper, the review of the IM-SRG, and so after the first development of the IM-SRG method, this became a very popular method in nuclear physics community, and that is how to say done by for example, this paper by Titus Morris made a great development to extend the reach of IM-SRG for heavier systems or multiple many operators. If we think about the independent flow for any operators, for this will be, SRG, IM-SRG scales polynomially, but it's okay, but the repetition of that is still very hard, so we need a better way. So they propose the usage of the so-called Magnus expansion, and if you construct the explicit calculation of unitary transformation here, this Magnus operator omega, this will give you a systematic way to derive effective operators for any other operators, other than Hamiltonian. And here I show some more practical form, giving you one time step forward calculation of omega s, like this. And you can truncate at some point if the nested commutators are norm on them are small enough. You can truncate at some point. So within this formulation of IM-SRG, all you have to do is essentially how to calculate the omega s, the Magnus operator. So that's the problem of our motivation or aim is to how to accelerate to calculate these omega operator with the help of, for example, machine learning or dynamic mode decomposition. So these are kind of two technical stuff. So let me just go through very quickly. So the point is hereafter. So any operators are kind of vectorized. So originally the Magnus operators are kind of tensor structures, but we can flatten them in a certain way. So you can vectorize it in a certain manner and taking anti or MST to reduce the number of elements to be kept. Okay, so let me begin with the first one, the machine learning approach to estimate the Magnus operators. And as you know, the machine learning techniques are becoming very popular, and you can find many examples in our field through, for example, this review article on RMP, or you can find some the collaborations of nuclear physics and machine learning like this, and this was held in the last May, and I watched this through YouTube. And so you or one may expect, if you feed in more and more data to neural networks, they run somehow underlying law or underlying physics. But as you may know, it is not usually the case. It is usually not the case. So we need to introduce some inductive biases in terms of, for example, the architecture design, or some more constraints into the loss function, for example, to get more closer answer to what you want. So one such way, one of the most known ways are physics-informed neural networks, PINs. And these figures from this review article on Nature Reviews Physics. And here, this shows the target system or target problem is the Vargas equation, and the physics. So these pins are used to solve the partial differential equation or ordinary differential equation. And what is done here is preparing the neural networks to predict u of x and t, and I mean the function of space and time for this equation. And so neural networks are trained to reproduce this u over x and t, given u and x of x and t at some point on a space and time. And the essential idea in the pins is to introduce additional those terms into the model. I mean, how this guiding principle or guiding PDE is satisfied with your prediction. I mean, if you take this u of x as our output of neural networks, and you can check how this Vargas equation is satisfied by just taking the squared errors on that. So as a natural expectation, so you want the neural networks model or any other models approximate, in this case, u of xt, respecting underlying equation or boundary conditions. But if you feed more and more data to neural networks, that will not be always helpful. I mean, and I would say, I have to say, adding this term is just giving you some soft constraints. I mean, actually they don't run physics at all. I mean, outside the region of the data, what I what you are doing here is the just some information, underlying information by imposing this first term. So this gives you just a soft constraints on the model. So inspired from this pins strategy, I have made some pin-based solver for IM-SRG, and this work was published in the PRC in the last year. And the essential idea is the same as I explained here. So the neural networks are trained to predict the Magnus operators in the IM-SRG, or something like this. And then we took just as like this, a very simple architecture for that. I mean, just having layers, having this kind of the OR connection. So of course, you can think about the replacement of the architecture to more fancier ways, but in some cases, it is I mean, enough. This very simple architecture is enough for interpolation or sometimes exploration of PD or ODs. And the essential idea is, as I said, to add the loss term on the derivative of the output. I mean, in addition to the ordinary loss terms like this, kind of the mean square errors on the omega s, and by differentiating omega s with respect to s, you can somehow get the ether, the generator for the IM-SRG transformation, and using these two terms, you can train the neural network to you can force them to respect somehow the underlying physics, or in this case, underlying means the IM-SRG Forward equation is a guiding principle to train the networks. And the loss function, the target loss function would be the sum of the ordinary loss function and the loss function on the ether term, and so this factor is kind of the balancing factor between the two terms, and the rule of thumb is to take the 100 for this problem. So you can make this contribution or kind of equivalent to each other. So here I show some results of the ground state energies of oxygen 16 and calcium 40 using IM-SRG net. Yes, a pin-based solver. So in the upper panels, you can see the energies of these systems with two different NN potentials as a function of S, and you can see these dotted lines shows the exact IM-SRG2 result, and the pale solid line in between the markers show the IM-SRG net calculation. Of course, you can not see the difference in the scale. So if you plot this difference in the logarithmic scale, you can find the IM-SRG net can predict or extrapolate within the 0.5 kb errors. I mean, you may say the calculation is almost converged around the 10 or so. So you can just stop out there, and what I'm doing is the boring stuff. You may say that, but it's true. If you are only interested in energy, I mean, what I'm doing here is to extrapolate Magnus operators. So you can get somehow some kind of the guarantee. I mean, you are doing right. I mean, if you are successfully extrapolate this Magnus operator, you can guarantee your success for any other operators through this the Magnus formulation of the IM-SRG calculation. So these are just showing some numbers. So just to confirm we are doing right, you can see that there are not only the energies, but also the charge radii can be, extrapolated very accurately. I mean, these are numbers for the charge radii at s equal 20 around here, and these are corresponding to the result at the right edge of these markers. So you can see the prediction errors are shown in both style, and the prediction errors of our method is much smaller than the residual to be gained through the less IM-SRG probe. So with this result, you can say you can just stop the R&D s equal 20 because your emulator can assist you to extrapolate from s equal 20 to where you want to go. And this is the typical point giving convergence is around 50 or 100 or so. So you can just save the, I don't know, 50% of your time or less than. Of course, you have to take account the cost for training the IM-SRG, so neural network, but you can gain a few tenths of percent of the calculation time. So here I show the running curves for this nuclei using two different NN potentials. And this shows these rosterns. Actually, what is shown here is the case for the number of data is equal to one case. I mean, we use just a single snapshot to train and the networks in each epoch. So this shows kind of our square errors on the Magnus operators for a single snapshot. And so we have used the training data from this point to 20, about 10 snapshots, and then you can predict from here, I mean, the S values giving convergence. So if you look at the dotted lines, the errors will be less than 1.10 to the minus 6 or so. So this means your Magnus operators are extrapolated or can be estimated within this error. So you can somehow ensure the correctness of your extrapolation for any other operators other than Hamiltonian. And I would say my method is not so smart, I would say, and it's very memory greedy because what we have done is to predict this Magnus operator directly. So these are connected to the neural network. So if you want to do that, you may need many copies during the calculation because you have to keep the computational graphs for forward propagation and also for back propagation in neural networks. So these are the number of elements of the vectorized Magnus operators with given Emacs truncation for basis. So you may encounter 10 to the 8th for the Emacs 14 or so, and this is very memory greedy. So actually, I gave up around the Emacs 10 with my computers. Okay, so the next part will be about the dynamic mode decomposition. So I have to say that this is not from me. I mean, the first work done in our community is their PhD thesis from your group, and I read this PhD thesis. So I have to say, so you in the MSU, so your PhD thesis will be read by many people, right? You should be aware of that. So inspired by this very nice work, so he has done the DMD operation emulation of the Hamiltonian matrix, and he has done the global sensitivity analysis on the low energy constant in the chiral potentials. So this is very nice work. And inspired by this work, I have implemented the functions to do similar but different. I mean the DMD emulation for Magnus operators in my package. So before going to that part, let me quickly go through the dynamic mode decomposition. So this is firstly developed in the fluid dynamics community, and you can decompose the dynamical system into the mode, dynamical modes, and one can reconstruct the original snapshot by doing this thing. If you take some snapshot of the dynamical system, the kind of function of space and time, and you can construct this kind of matrices having the snapshot as its form, and you can also do the similar thing for the one-time step forward, and of course the relation between the x and the x prime here is in general very nonlinear, but in some cases, in some cases you can effectively approximate this one-time step forward state by just a linear operator like this, or linear operator A. So let me introduce the DMD algorithm for our IM-SRG flow. So these are a little bit different from the previous slide, but forget about that. So if you take some n snapshot of your system, you can vectorize them into this, for example, this small x1 or xn, and you can construct this d by n matrices x, and you can also construct this y one-time step forward. And of course, as I say, the relation between these x and y are in general unknown and non-linear, but in DMD, you approximate this non-linear map by linear map A. So it seems too much, simplification or approximation, but sometimes it works well for some systems. So here, the D is, so suppose the D is the dimension of the many-body operators, like in Magnus operators. So you will have kind of more than 10 to the 7th or 10 to the 8th or dimensions. And the number of snapshot would be 10 or 1,000 if you like. And you can construct this snapshot, or say, and you can say this, sampling or sample point or training point. But anyway, so you can construct these data matrices. And what you will do is the SVD of this snapshot. So this could be exact, but you may want to truncate the SVD by truncating the important and the singular values. And then you can compute a matrix A like this, or connection between x and y in terms of y and the Møller-Plesset pseudo inverse of x in this way. And of course, you can introduce some approximation for that, and then you can get this kind of expression for your linear operator to approximate the one time step forward operator. And then finally, you can get some kind of latent expression. I mean, they obtain the time evolution operator in a latent space by applying the UR appeared in the SVD from both sides. You can construct this A tilde. This is so. If you look at the relation between A tilde and A, you can regard this UR as encoder and the decoder that is frequently seen in the machine learning techniques. And after that, you can think of the k time or multiple time step forward using just the power of kth power of this A tilde. You can you can make the time evolution in a latent space using this tilde A. And then finally you can recover the original vector or original state vector by applying UR dollar. So you can get in principle you can get the prediction at some far place. So this is the idea of the DMD algorithm. And so here I have introduced some approximation for the SVD. So you may think the DMD, so you have to introduce kind of the threshold for the SVD, and if you take it too large value, and this will lead to not enough capturing the important modes, and if these values are too small, you will get kind of noisy prediction due to the numerical error. So the rule of thumb of the current system is to take 10 to the minus 6 and leading to the very low the several rank from the snapshot. And okay, so let me go through quickly. So this figure shows the flow of Magnus operators. I mean, the Magnus operators are very high dimensional vectors now, and these are just to take 40 samples for each. I mean, the one body part and two body proton part and the two body proton neutron part out of 10 to the 8th elements of the Magnus operators. And if you take the snapshot from the very early stage of the IM-SRG flow, your prediction using DMD shown by the dotted line, dashed lines are this kind of their scattered predictions. And if you take more snapshots from S1 to 10, your prediction looks nice. But if you take this predicted or emulated Magnus operators to calculate the energy, you will get this kind of behavior. These green, if your emulation is perfect, your predictions using DMD snapshots will be on the green lines, but obviously your calculation is wrong. I mean, not decreasing as a function of S. But so this is partly because your snapshot includes very nonlinear behavior here. So our DMD are kind of struggling to explain that. So if you discard them, I mean the early stage snapshot, you can get slightly improved results. Or the prediction at the S equal 20 is kind of okay, but you still have the problem of like the non-decreasing energy as a function of X. So nonlinear nature of IM-SRG in the smaller region of flow parameter make your calculation bad. And if you feed more larger S data to DMD, you can get even better results, but you still have some deviations. And I have to say, it's very non-trivial to take snapshot from where to where to get the results, I mean the accuracy you want. So let me summarize the current status of the two emulations for IM-SRG. I mean, especially from the extrapolating in Magnus operators. I mean, IM-SRG net have some nice features. I mean, the rush S-limit is kind of under control because of the nature of the activation function. So if you put the S1000 or 10,000, it will give you the same result because of the asymptotic behavior of activation functions adopted in neural networks. And but the model is very greedy, and the acceleration effect is very limited because of the computational time to train the networks. And the DMD is very nice because it's very fast, and we can see the low-rank structure of Magnus operators, but you still have some problems about the exponentiation of H-tilde. You may have some unstable behavior, even if the eigenvalues of H-tilde is almost within the cycle, you encounter this kind of behavior, or you will get the divergence in some cases. So both works fine for kind of linear part of IM-SRG, and the next step will be to develop a method dealing with linear part or the early stage of the IM-SRG probe and the HF-MBPT force. Okay, so let me summarize. First, I have talked about the jury package for nuclear structure calculations, and so far the functions are kind of for my purposes, and now I'm writing some codes for quantum computing. What will be needed for you? So or you have some ideas, or if you are interested in, please tell me. And the second part of my talk was about emulators for IM-SRG. So I have tested the machine learning techniques and the DMD to predict the Magnus operators as a function of probe parameter by taking some snapshot from the early stage of the IM-SRG. So if we could I would say predict very well using this method, it will be very nice for deriving effective interactions or deriving effective operators for to extend the reach of the ab initio method or global sensitivity analysis on chiral potentials, for example. And then we have seen the both work fine for rather linear part of IM-SRG probe, and but we have seen these are kind of complementary to each other. So our next step will be to combine them or to learn the nonlinear part of the IM-SRG probe. So our ambition is something like to find a latent space or latent representation of nuclear many-body wave functions or operators. I mean, these are typically 10 to the 10s or more, but we may have some chance or ideas to compress them to a more compact form, I mean, or to express the nuclear many-body function, wave functions of operators. So this is just the beginning, I mean, at the beginning for this survey or this journey. So, okay, so you have.
Just like speaker first. There should be a lot of questions because the people here, some of them actually working on DMDs, neural net, machine learning stuff.
Two questions. One is, what is the role of the density dependence review from?
Density dependence. So you mean something relatively very small? Yeah, density dependence. This is from the momentum space expression of cerebral force. and we use the normal nuclear density to, sum over the 3 nuclear lengths.
Okay. And then how does it propagate on the other densities?
Other densities?
Yes. You always use one density.
Oh, yes.
Okay. Second question is, in the SVD, do you run into violation of positive definiteness, or is the RD instability similar to that issue?
Yes, but the positive definiteness, yes, related to this kind of the inversion, but yeah, we truncate at some point. The singular values at some point, so we can somehow deal with that.
Okay, just small. Yeah.
But the how much value you should take is very non-trivial.
Okay.
Other questions? Yeah, I go first. Yeah, go ahead.
Oh, me?
Yeah.
Okay. If you read Jacob's thesis about doing DMD on IM-SRG without the Magnus expansion, it worked pretty well. So what do you think changes when you use the Magnus expansion where DMD has problem predicting flow to larger S? What do you think changes from the Magnus expansion?
If I understand correctly, the Jacob's paper, that emulation is from 0 to 1 or so, right? Very short-term predictions, right?
Oh, so you, okay.
Yeah, and what I've done is to kind of long predictions from these points to these, giving convergence of the IM-SRG calculation. So this may make some differences.
But do they see like the eigenvalues larger than 1 in the previous studies?
In the previous studies,
In the what's the name? Jacob's thesis, do they actually see the eigenvalues outside of the circle?
I don't remember.
Because that would be makes things unstable.
But yeah, yes, that's right. So I naively thought this kind of plot can be used as a diagnostic for the convergence. Of course, we can do that, but it doesn't guarantee the convergence to the exact values. Even if you have the eigenvalues within the circle, you can get this kind of behavior.
So have you ever tried to do this with other operators, observable operators, like the deriving?
Using the DMD.
And the teams.
I have not tried that, but I will do that because the reason is partly because of my regionness. I have not implemented the non-scalar operators in my IM-SRG part. So, but I will check by calculating charge radii, for example. Yeah. But the answer is I have not checked that.
And the dependence, you should very nice plot that the difference between the DMD and the exact solution, right? So do you think that difference will change if you change the interaction to make it softer, or you use a smaller model space? That means convergence could be faster. Then this kind of deviation could be smaller.
So in conclusion, I have no idea. I have not checked that, but yeah, it will be very nice to see.
Heiko.
I can comment if I properly heard John Joe's question just now. So we tried it in the Hamiltonian version of this for AV18. It works beautifully. I thought we would break it, and it didn't care.
So AV18 is more hard, right?
Yeah, AV18 is terrible in terms of many-body convergence, but I think the key is you're essentially looking at the projection of AD18 in a finite model space. And the DMD learns whatever is in that finite model space perfectly. It's just like it cannot learn anything that's not in that model space. Right? So the model space puts a cutoff on, and that is enough for the DMD, but of course you cannot recover the physics that would be missing from stuff beyond the model space that you included.
But how about the model space, the transition? If do you think in a smaller model space, the DMD can work back?
But I mean, it did work fine from anything from Emacs 6 to 12 with AD18. It learned what happened in the model space perfectly fine. It's just that we know that that model space is not enough to really capture the physically converged energy.
Okay, the next, yeah.
So you truncate the SVD at some tolerance here, 10 to the minus 6. How does the performance change when you vary that threshold?
For performance.
Yeah, so like if you decrease the tolerance, if you include more singular values, do you still see this divergence from the truth value?
Yes, if you the decrease from this value, you will get the divergence behavior in the DMD prediction. So, but if you go up, I mean increase this value, that doesn't much affect. I mean, 10 to the 5th is almost similar to this case. I mean, this risk is just picking one additional, or just missing one or two.
Online, do we have questions? You guys go ahead. Okay, so Kyle actually raised his hand. I'll hear it. No more questions? Let me ask one naive question. Okay, you have this error plot versus epoch. The error plot for the versus epoch, like training. Yeah, that's fancy.
Epoch, yeah.
That
Yes.
one. Why is error for larger Emacs actually smaller?
Because of simply the dimensionality, I think. I mean, naively speaking, the size of element will be smaller for larger Emacs, I think.
I mean the values. You mean the omega values are
Yes.
smaller?
And the absolute values become smaller, and these will be kind of squared. So
this
you will
is
get
okay. So these are not the relative errors. This is actually the absolute errors for the omegas.
yes, or the squared
Okay,
values.
that makes sense. Okay, if no more questions, let's thank the speaker again.